Welcome to this presentation on impulse response, which is a very important topic. We will derive the impulse response in this presentation. We will also point out why it is important. Let us consider the linear time invariant system. The input is delta, the output is G. Remember, this is how the impulse response is defined. Now shift the input, as it is time invariant, output will also be shifted. So you get this G of n minus k. Notice that if it is not time invariant, you cannot use the symbol G here, okay. So here we assume that it is time invariant. Of course it is also linear. Recall the explanation that we gave earlier for time invariance. Now let us look at the expression for impulse response of linear time invariant systems. Recall this expression that we derived earlier, where u is decomposed along the directions of the impulse signal, and this u of k is the value that this arbitrary input sequence u takes at different time instances. So u of k is the value that it takes at time instant k, and so on, okay. So u is a linear combination of sequences of the form delta of n minus k. You can think of this as this sequence multiplied by the scalar and added across all k, going from minus infinity to plus infinity. Now because it is time invariant, delta of n minus k produces G of n minus k. So the question is, if the system is linear, I use a linear combination of this, I would expect the same linear combination of this. So this is what is written here. The output corresponding to this input u is the same linear combination of responses due to delta of n minus k, that is, which happens because of linearity. So we obtain y of n to be the same linear combination as given in this expression. This is obtained as a linear combination with u of k multiplying this. The same u of k should multiply here because these are all scalars, that multiplies the corresponding output. Delta of n minus k produces G of n minus k. Now remember the rule on argument. The sum of these two arguments should be equal to the argument on the left hand side, which is n in this case. Now we define this, recall the symbol which we stated in one of the earlier presentations. This is written as u of n asterisk y of n. We say that u of n convolved with y of n, u of n, y of n being doubly infinite sequences. So when I write like this, which is a short form, what I mean is this. This is the notation we will use in the rest of this course. So argument on the left hand side is equal to sum of the arguments in the sum. Alright, this is a very important result. We will use this repeatedly in this course. Now we will take an example. We start with the expression from the previous slide, and it is given that the impulse response is as given here. Both of them start at n equals 0. Here G takes the value 1, 2, 3, U takes the value 4, 5, 6, and they are 0 for n less than 0, and of course it is also understood that for wherever it is not specified, what happens after 3? It is 0. All values beyond this point are 0, so they are not specified. So let us calculate y of 0. We have to substitute here. The only combination that gives rise to 0 here is obtained by u0 g of 0. Remember, these values are 0 for n negative because they start at n equals 0. This sequence starts at n equals 0. Before that it is all 0. Similarly, before here u is 0, So for negative values it is 0. Only way we can produce 0 as the sum is if we allow both u and g to take 0. So we obtain the value to be 4 by multiplying u of 0 is 4, g of 0 is 1, multiply this you get 4. What about y of 1? Okay, you have one combination u0 g1, another combination u1 g0. Once again negative arguments means we do not have to consider, so we have to multiply. So if you multiply and add you should get 13. What about y2? Now you have u0 g2 plus u1 g1 plus u2 g0, other terms are 0 because those terms will involve negative arguments, or they could involve arguments greater than 2. Remember we have non-zero values only for 0, 1, 2. So this value comes to 28, you can verify. Similarly you can calculate y3 to be 27 and you can calculate y4 to be this. For y4 also there is only one combination that is possible. So we have extensively used this formula, the rule that we used, namely sum of these two arguments you should get the argument on the left hand side. All the terms that do not appear above are 0. We calculated for values from y0 to y4, all other terms are 0. So we do not have to consider them. Let us now go and see a Scilab code that implements this. I also have Scilab here, I will demonstrate that. I have already opened Scilab and the file is called con2.sce. Let me execute it and you see that the value is obtained here. The values are 4, 13, 28, 27, 18 as we obtained earlier. Let me just scroll up a little bit and you can actually see the values of h and u. These are as per what is given in the example. So let us go back now. Okay, I am going to point out the importance of impulse response now. This is the expression that we derived earlier. We can compare term by term and obtain this. Notice that this multiplies an doubly infinite sequence. So each one multiplies a doubly infinite sequence. So we take out just g of n minus k from there and so you write y of n, we can get this expression. Remember u is arbitrary. We never told that u has to be a step, u has to be a ramp, it has to be a sinusoid and so on. U is arbitrary. Until now we discussed only two standard sequences, namely impulse and step. This is an arbitrary sequence u of k. So the impulse response has all information about LTI. Why? Because supposing I ask you a question, what will be the response if I give the input as some arbitrary u? Well, you will say just give me that value u, I do not have to do that experiment, all I have to do is to use this formula because I have this g. I will evaluate this convolution and that will be the output. So it does not matter what input I will give, you shall use the same formula, all that you need to know is g. If you know g, you can give the corresponding output without doing any further experiment. So we say that the impulse response has all information about this LTI system, linear time invariant system. Recall why LTI? We are using the same g because it is time invariant, we are using the same linear sum, we are using the same linear combination because it is linear. So it is linear time invariant system. So impulse response has all information about this LTI. Given an impulse response, we can determine the output due to any arbitrary input. We will further consider the impulse response and its importance. To get the impulse response, one needs to carry out only one experiment. Okay? What is that? For the LTI at rest, that is, you take the initial condition to be 0, so that it is linear from input output perspective, give an impulse and measure the output, that is, you measure g of m. Okay? Mind you, you have to measure only g of m. You do not have to measure g of n minus 1, you do not have to do another experiment at n equals 2 and so on. You have to do the experiment only once and only once. That impulse should come at n equals 0, you just measure the output, you call it g of n, that is it. If you want g of n minus 1, you just shift it by 1. You want g of n minus 2, just shift it by 2 and so on. So you have all those g's available to you, then you calculate, you do not do the experiment, you calculate the output for any arbitrary input using this formula. There is no need at all to do any other experiment. So we say that the impulse response has all information about the system. This brings us to the end of this presentation. It is an important concept, impulse response. I urge you to go through this and understand the topic presented in this presentation. Thank you.